Hi guys, welcome. This is module CM4269, Green and Sustainable Chemistry, and this is really a topping and tailing lecture. We're going to think a bit about safety, risk assessment and solvents, and top it off with a couple of case studies. This probably will be the last lecture in this series, I think. Okay, so I won't waste time particularly on the order of stuff. We're going to look around some implications of principles 3, 4 and 5 about safety, solvents, and we're going to move that and bridge then into ionic liquids, which we haven't talked about in the course, but they're actually really quite interesting and we should look at that. We'll then touch on some case studies and particularly close with a case study on biofuels, which involves supercritical solvents, supercritical liquids. Yeah, and then call it a day, I think. Reading for this twofold, Lancaster various chapters and the Green Chemistry Theory and Practice by Anastas and Warner. Okay, I think probably we're there. So let's start thinking about the principles and some things that flow from those. So we're interested really in 3 of the principles. Principle 3, which is about less hazardous syntheses. Principle 4, about designing safer chemicals. And Principle 5, about using safer solvents and safer auxiliaries. Okay, just to remind us, here are a more formal statement of those principles. I won't read that. You've already seen these previously. The issue here is how actually do we know whether we are actually mitigating risks or making things safer. There is a tool called risk assessment, and we're going to talk now about risk assessment and mitigation. Basically, the lower the risks, the safer the processes, which means the safer the industry. Right, moving on. How do I say this? Stuff doesn't just happen. You've got a safe process, you've got an economic process, you've reduced your emissions. That stuff doesn't just randomly happen by accident. What we're going to do now is look at the type of structures and systems which we can use to deliver good risk assessment and good risk mitigation, so that the things we actually do want to happen do happen. So things just don't happen. To deliver business outcomes, and safety is just as much a business outcome as profit, we use business systems. So business systems that you know about are sales systems. Business systems you know about are maybe environmental management systems. Business system that you know about now is risk assessment and mitigation. Be it financial risk, be it business risk, or be it safety risk, chemical risk. So the types of systems that this goes alongside of in terms of business plans, profitability, safety, quality assurance, environment, communications policies, policies on image, all of these things are all tied together in the way that the business runs. So things don't happen by accident. Actually, you have business systems to deliver desired outcomes, and risk assessment and mitigation is one of those business outcomes, business systems, which clearly you want to deliver. Okay, here's a pretty picture. Now, I'm going to walk you through this. This is actually a risk assessment and mitigation system for machinery. Now, I know that chemical plants have machinery. I've not chosen it for that reason. I've chosen it because it's a really neat little diagram, and actually it's pretty much analogous to how we operate in the commercial industrial sector, the chemical sector. So it's worth going through. Okay, so this is about machinery, we know that, so we start up here, and first of all we understand what the limits of the machine are. We identify the hazards with the machine, and this is important now. To identify the hazards, you have to know what people are going to do. So you've got a brand new lump of kit there. If all it's ever going to do is sit on the bench and grin at you and wink its little green lights, probably not much risk. If you've got someone there, on the other hand, doing all sorts of things and using this equipment, now we're thinking of machinery on a factory floor, so yeah, think of putting hands into moving parts, think of long hair getting caught, just to visualize it. Only when you've got what people are going to do can you identify hazards. Then you can identify the risk. A hazard is something that may or may not happen. So Hong Kong being hit by a 50-meter tidal wave, for instance, it may be a risk, but it's likely not to be a very large risk. Then risk evaluation. So first of all, hazard identification, risk estimation, risk evaluation. The sort of standard things that you'd expect to do when you're thinking and estimating risks of a process. So now we're more quantitative. We've evaluated the risk. Now, the sort of question we now have is that risk, once it's evaluated, is it either below a threshold that the company, the organisation or the law have set? So is it, it's still a risk, but is it okay? Or actually, does it have to be reduced? Now we go round and round a circle here. If actually it's below the threshold or it's been reduced, we can say yes, and that's the end of our process. If on the other hand it's not below the threshold or it hasn't been adequately reduced, the answer is no. So then you look at three headings if you want. Inherent safe design, use of safeguards, use of information. This is about equipment. So is the equipment inherently safely designed, or actually do we need to go and get another model which is a much better and safer design? If it's reasonably safe, are we using all the safeguards? And we're talking factory floor, so we're talking about cut-out guards and things like that. So if you put your hand in, the guard cuts the power to the machine or whatever. It's easier to think in a machinery type of way about this sort of thing before we get to talk in a chemical process about this sort of thing. And use of information. Are the people using this equipment or running this process informed enough. Okay, so that's our analytical framework for this. The result of this will be to increase either the information or the protective measures. Are the protective measures dependent on a control system? If the answer is no, so you've thought about this, you've improved safeguards, you've given information and maybe modified the system, you come up here and you then ask, are there other hazards you haven't thought about? If the answer is yes, then you go back through here. If the answer is no, you come back to the same question, has it been adequately reduced? And maybe the answer is still no. If you can't get it below using this loop, whatever your standard is or the law says, then actually you've got to think about the entire process. Should you be making this stuff or whatever? Or if you can't find a safer machine, we're going to have to think about redesigning the process. Now, we're talking about machines mostly here, so often the protective measures are dependent on the control system. If they are, then actually there's a number of international standards and things which can be used, and you would then use those to guide what you're doing. This is actually the equipment engineering ISO standard which you would use. So you have basically a loop system which, provided you can get below the threshold, that will improve the safety of, in this case, a piece of machine. And again, you have a number of components, reasons why you might want to be doing this. Okay, rather than look theoretically, let's now look at a real system, the Konica Minolta system. It's Konica Minolta are a fairly seriously sized chemical company, and we're going to look at a couple of parts of their system. Now, risk assessment is based in processes. Unless you understand your processes, you can't do a good risk assessment. So some of you last year in 3292, well, when you do that, if you're doing it now, you will do your own risk assessments. That means there's a much greater requirement before the practical ever starts for you to look really carefully at what you're doing and understand what you're doing in a way which will allow you to do the risk assessment. And if we're thinking about a company, risk assessment starts long before your materials arrive or your equipment arrives. Anything you bring into the factory contains unknown unknowns. For instance, your raw materials, you've got to know how pure it is, what impurities it might have with it for any given chemical process. So, therefore, the risk assessment system starts with your procurement system, the system you use to buy things. And this slide is actually about databases, because what this is really about is any good procurement system will reduce your risk, it will mitigate your risk. But for these systems to run, you need databases. So let's just walk through this a little bit. So you want to buy something new, some new material or whatever, or maybe you're making a new product or designing a new process. Your main database here contains information on the parts, the raw materials, the chemical content, manufacturer information, and that database is interactive. So you can view certain processes or things you're doing, or you can calculate modifications, development and design. This is probably one of the keystone systems you need. Now, and of course, this system is also the one that provides information to your customers or to other companies or maybe even your supplier companies. So what sorts of things do you do if you're thinking of a new process or assessing an existing process, new material? First of all, you can request a product constituent survey. So it's the parts and materials, the manufacturers. If it's a material from a new supplier, then you're requesting it. You're requesting the same information from them and compare it to your requirement. Okay, we have all these systems are joined up, so you get confirmations of that request. You have smooth web-based communication systems to ensure compliance. And eventually you'll get a response from your manufacturer supplier, and then the information is registered in your system, so actually you can establish whether whether you can use that product. The important thing is you need to have a good database system. Let's begin to take a particular example, because it still is a bit woolly. Let's decide that you're thinking about solvents, and if you're thinking about solvents, you're going to be thinking about VOCs, reducing VOCs emissions and things like that. Possibly you might wanting to be swapping a solvent for something like an ionic liquid, which has much lower emissions. So you're maybe looking at a change to the process. So we're going to move on now into this company's systems, and we're going to look more closely at this particular example of reducing solvents and therefore reducing VOCs. So, okay, we want to change part of the process. It's called a risk verification process. Now, you have gone and got your new candidate materials. Maybe you're trying to put an ionic liquid in instead of a solvent or whatever. Or maybe you've just got the same material from a different supplier which has different standards and different impurities. First of all, your company, and Minolta are no exception to that, they have a substance register which has those substances in it that have been disallowed on the plant for either safety or legal reasons. This is a live system, so it's updated in respect of new information, new research, new developments. So, first of all, is your candidate material on this list? If the answer is yes, the process gets very short, because you look again on the risk controls by the Safety Screening Council or whoever the body is, and if they are all okay, then actually the answer is no, you can't change the process that way, or you can't buy in this new stuff that you were looking. If on the other hand these decisions and controls are in some way faulty or not as good as they should be, then actually you can reassess the system, if you like, what's on this register and why it's on there and how it's on there, and then make changes here, and it then might be possible, if you assign rigorous control standards, to approve it for use. But let's imagine at the moment that it isn't on this big no-no register. You then, exactly as we were looking at just now, you quantify the risk. If it's below the reference value, it can be approved for use. If you're changing the conditions of use or changing the material, then actually you reevaluate the risk with that new material down here. That may or may not yield you additional control requirements, and you're in business. If, however, the quantified risk is above the reference value, then you go round this loop until either it can be approved for use or it's unapproved for use. Good. Okay, so that's all plum and dandy. The next stage is we're moving into, if you like, the particular example of VOCs. Because if you're lowering the solvent use, you're lowering the VOCs, and that's a very valid thing that you might want to do for environmental or health reasons. Okay, so Minolta have, for a number of years, been trying to reduce VOCs. VOCs have a whole bunch of health risks associated with them and environmental risks. They've developed their own environmental impact index as part of their environmental plan, with the specific strategy or policy or aim to reduce the direct risk to human health and the risk of atmospheric pollution. And in financial year 2012, VOC emissions since 1993 were down. They started in 1993. Since 2005, so they've had 7 years, were down by 75%, which that may or may not meet their plans. We'll have a look in a moment. This is an example of how the systems themselves have been able to produce change. Part of the pressure here wasn't just to do with Minolta going, oh my goodness, we must reduce VOCs. It was regulatory pressure, financial pressure on the company. Okay, but let's now have a look at some results then. So these were the solvents they targeted, and hence the VOCs they were aiming to eliminate. And clearly, in 1993, all of these substances were in use as solvents in their plant. So they had a rationale for selecting these solvents among the many others, and their rationale is actually fairly easy to see. You've got some major carcinogens and some very, very harmful substances in here. So they looked at the health impacts of what they were using, and that developed their rationale and their timetable for how they were going to eliminate these substances from their processes. Of course, that means every process that involved those substances had to be modified, had to be changed. And here you have a list of what they chose, and they obviously, as part of this system, apart from the rationale and the identification of substances, they had a recording and verification system. So trichloroethylene, completely eliminated by 1998 in all Minolta activities, and so on and so forth. We go down this list. I won't bother to read it out to you. They developed their own system for establishing how dangerous or what the risk was in terms of these solvents. And again, I won't go through it, but they developed their own hazard coefficient, and this gives you some examples of what substances were on there. And they basically had a strategy that they were going to remove substances in these sort of hazard levels. Now, the system is self-perpetuating because their aim was zero VOCs, or at least minimal VOCs. They did the measurements outside of the factory gate and inside the factory in the plant, but outside where local people were living. This happened in Japan. I won't worry you more with that. That's not something that will worry you. It's simply how they did, how they constructed their hazard coefficient. Let's look at some measurements at their verification system. Okay, so here is their hazard index points. Back in 2005 it was at 5,000. Their hazard rating by 2012 was down to about 1,200. Their target, their policy, which is what this is, it's a policy example, was actually about 1,500. So they had met their 2012 target. They then have more targets going on in future years to further reduce their risk profile, VOC emissions. Now, of course, once you meet your target, you then look at the target and work out where you're going to go next, what the next 5 years targets are. And this is an analysis of that. They wanted to reduce their impact by 70-odd%, and they reduced it by 75%. So that was a self-assessment. They achieved their goal by 2012, so that's all good. Where are they going next? What are the next targets? Well, they will look at the next tranche of VOCs and target those in a similar way. Now, obviously, their system now has in it some of the solvents, all of the solvents that they've actually eliminated, so they can't then reintroduce them. Okay, so I think we talked a bit already about how things don't just happen by accident. The risk assessment system is actually a normal business system, and alongside these types of systems, it runs throughout to make sure that profit is maximized, safety is maximized, risk is minimized, and stuff like that. However, it's fine to say that, but to do any sort of risk assessment, it comes down to a detailed knowledge at the process level. The example I gave you earlier about your risk assessments in 3292, for instance. For those of you that normally just get the script, you have the pre-lab and you try to answer the pre-lab from the script, this is entirely insufficient for those practicals, as you will probably have discovered. You need a detailed, intimate knowledge of your process. So let's actually think about what, in this example, what information they needed to actually reduce their VOC levels, their solvent use. Okay, here's a list. They've got the atmospheric concentration on there, and you might think, oh, that's all we need. Actually, not. Solvent concentrations in the atmosphere are, of course, essential, but it's dose or exposure which is the real key knowledge that's required. So you do have to measure the solvents, but if you're measuring within a sealed, isolated environment where the people are outside of that environment and you've got high solvent concentrations in the environment, where's the problem to human health? So it's what's actually happening, what people are doing, how much they're breathing or how close they are to it, and the type of information. You need to have the no observable effects level. That is the level at which there are no effects that can be observed with people. You need the lethal dose, the LD50, the lethal dose at which 50% of the population will die if they're exposed to that level. You need threshold levels. You need time-weighted averages of concentrations in the vapor phase. You need the flash point, and you need to go through the risk assessment process to look at technical substitution or hazard mitigation and the impact that has on, dare I say it, the economics of your process and your business and your profitability. Because it might be that this sort of consideration leads you to the conclusion that to put this process right, the risk currently is unacceptable. To put it right, it becomes entirely non-profitable. We will stop making this product. We will stop running this process. Okay, so let's now move on to solvents, which is still what we're talking about. Solvents have a number of roles as a reaction environment, reactant, as an extractant, dissolution, recrystallization. And typically solvents determine the purity of the product, the final products of the properties of the product. So for gloss paint, the degree of gloss is dependent on your final solvent concentration. Also, you need to think about the end of process recycling, and of course what we're talking about, VOCs, hazards and safeties. So let's actually look at solvents, and this is a diagram I've stolen. The web address is on there. We're trying to limit VOCs. Minolta, we're trying to limit VOCs and solvents. So this little diagram, if you like, is a reprise of the types of problems and properties that solvents have. Their dissolving power depends on molecular forces, things like this. They have major effects on human health. This is just a little summary with symptoms, and those how badly one is affected is going to depend on dose, potency, route of exposure. Some of these properties, okay, you have toxicity in there, flammability, environmental impact, but the colour and the odour may actually be less important properties, but all of the rest of these properties contribute to the right hand side of the diagrams. So basically, solvents are not the nicest of substances. If we think about mitigation of their effects versus avoidance of their effects, green chemistry, that's the way our thinking will move here. So what would be the ways ahead in these circumstances? Solvent-free processes, we're going to look at them in a moment. Benign, non-volatile volatile solvents, ionic liquids, and we have a list of things down here. We probably will always have some organic solvents, but we hope less, a lot less. So for the shape of most of the rest of this lecture, we're going to now go through these headings one by one and see how they can contribute to our safer systems. And effectively we begin to leave the risk part of the lecture behind at this point, and we're now talking more properly about solvents. Remember, benign solvents, non-volatile solvents include water, and we talked a bit about that before. Okay, so our first thing was having non-solvent type systems. Well, okay, Here is one. Methyl tert butyl ether, major industrial solvent, used in a number of processes. You can make it all in the gas phase. If you use methyl propene with methanol over ion exchange resin, an acid ion exchange resin, actually you can make this with no solvent at all. Well, methanol is the solvent, but it's also a reactant, so you just keep moving it around. So, there you go. Using a gas phase catalyzed process, you can very largely remove solvents in a great number of really quite basic and important product manufacturers. There's a spectacular example called Raiston synthesis, where instead of using a solvent, you actually directly react your solid reagents in a, if you like, in a ball mill. So you're doing it initially. Actually, some of these reactants, not solvents, are liquids, but the product becomes solid. Let's have a closer look, and you might be somewhat surprised by how this works. So we basically have the production of a really quite complicated reaction. And before we go down this line, I should tell you that the solvent-free, so a grind is basically, you've got it in a ball mill, you've got no liquid there. The solvent-free method of synthesis here has quantitative yield. If you do it in solvents, as it's traditionally been done, the yield is about 50%. So this is one example of a very, it's not a simple product, but a solvent-free method of making quite complex products. You start with your sodium hydroxide, acetylpyridine and benzaldehyde, and basically you do a grind. It sounds a bit of an odd way of putting it, but basically you're in a ball mill and you do sequential aldol and then Michael additions, and you steadily do one grind after the other as you build your product up. Now, what are the advantages here apart from having no solvents generally? Well, actually you can even save stages. You don't need to recrystallize and purify before your final step. So yes, you're saving solvent, but you're saving steps as well. So you've got a double saving. You basically have quantitative production of your product with very little else. So solvent-free, that was the heading we were thinking about. And we've had two examples, gas phase catalysis, or actually, in this case, a dry grind. Sounds really quite unpleasant. Now, the next heading was benign or non-volatile solvents, which of course includes water. We've talked a little bit about this in the past, so we know Diels-Alder's reactions in water can be faster than in traditional solvents, and I'd refer you back to the material we did there. Aqueous-based catalysts, organic transformations in aqueous systems, organometallic carbonyl condensations, and we've actually looked at some of these previously as well. Multi-phase droplet reactors. An example might be free radical bromination of organics in aqueous systems. Have a look at these references, very nicely described. Now, benign non-volatile solvents include ionic liquids, but I'm not going to talk about them here because they are the next heading after we've finished benign and non-volatile solvents. So, what makes a solvent volatile? And what makes it benign? Well, basically, the less volatile it is, the less VOCs there are. That's one of the major measures of benignness. So, immobilized solvents. THF, tetrahydrofuran, it's a very commonly used solvent. Boiling point 65 degrees centigrade, freezing point about -17. So it's a solvent. A solvent's solvent. It's volatile. It's got all of the normal problems. Well, if you use the polymeric version of tetrahydrofuran, clearly the molecular mass has increased hugely. It's incredibly less volatile, yet it has pretty much the same solvation properties as the THF based solvent. So that's another approach. Actually use macromonomers and synthesize the polymeric form of your solvent, providing it has similar solvation properties and gives you a similar reaction environment. Then actually immobilized solvents are a very good way to go. Okay, so now it's a new heading, solvents and ionic liquids. Let's think about ionic liquids. Now, what do we know of ionic liquids? Well, the most probably obvious one is molten sodium chloride. That's a good ionic liquid. It's a liquid which is ionic, which is not aqueous. So molten salt is a good ionic liquid. Unfortunately, not quite as good if you're trying to do organic synthesis. So effectively, there's a whole range of ionic liquids which are actually all available. You can buy them, or at least you can buy a number of types of ionic liquid, and they are surprisingly in quite widespread use. There's a lot of interest in green chemistry in these ionic liquids because, well, we'll see in a moment, you can actually engineer the reaction environment, which is pretty good stuff. So, how do they work? I'm going to think of them as solvents initially, but then we'll look at their roles also as catalysts. Basically, you have charge separation, but very poor packing of the ions. These aren't going to form a crystal any millennium soon. They have, because the two ions are held together by electrostatic attraction, pretty much no vapor pressure. The downside is there's a number of downsides. They're often water or air sensitive, so you need to think carefully about the conditions under which you use them. And you can see the types of structures, and of course you can modify chain lengths, you can modify cation to anion ratio. There's a whole load of things you can do when you're making these things. Okay, so although water has clear advantages over organic solvents, ionic liquids also have clear advantages over organic solvents, but not quite as clear as water. We're very early on the road for ionic liquids. So there are some syntheses which are very straightforward. You can just make these things really potentially easily. Some, on the other hand, are quite complicated. So ionic liquids, you're moving a whole load of process out of your process upstream to before it comes into your gate, because you're buying them. So solvents are still used to prepare your ionic liquids. It's unlikely you'll be preparing your own ionic liquids, you'll buy them. Very high purity is required. Chloride corrodes steel. So you've got to be very clear that all of your chlorine in here is tied up in the ionic liquid, not with appreciable amounts of impure chloride ions kicking around, for instance. The environmental impact of a lot of these liquids is poorly known. So yeah, you've got no vapor pressure, which is going to help you, but what about the rest? They're negatives. The positives, you can tailor make your reaction environment. When you're using them as catalysts, by doing exactly this tuning, you can actually tune catalysts. So tuning catalysts, tailor making reaction environments, they're quite powerful attractants if you're doing green chemistry. The main negatives are we don't know as much about them as we'd like, and effectively you're moving your emissions upstream of your process. There's not been very much cradle to cradle or cradle to grave work done on these ionic liquids, but you can do very exciting things with them. Okay, let's give you a couple of examples. The ionic liquid here is providing a reaction environment as a solvent. So for instance, a Diels-Alder reaction at room temperature, 75% yield. There are a number of applications where you can use ionic liquids to replace Lewis acids. MIM, for instance, there she blows. So you have as the anion an aluminium chloride. Now, it's part of the ionic liquid, but you can use it. It can be used effectively in the reaction as a Lewis acid. So, again, really beginning to be really clever stuff. Other examples, again, the ionic liquid, the key is in the previous slide. Room temperature, 98% conversion. Again, with this type of reaction scheme, and again 99%, and again you get some control on structure. Now, control on structure is for many syntheses as important as the synthesis itself. It's why you're doing it. So ionic liquids can be used and are used to be enantiomer selective. So and now we're moving, if you like, into the catalytic side of ionic liquids. So again, I won't worry, but you can see you've got what looks like a Lewis acid in here as part of the ionic liquid. Enantiomeric efficiency of 80%, one enantiomeric form over the other. And again, examples here very much refer you to the references where you'll find them discussed. For a chemist interested in synthesis, to be able to engineer the reaction environment, that's just using ionic liquids as solvents, but also to potentially use them as catalysts in their own right, tailorable, engineerable catalysts. Watch this space. Ionic liquids are potentially one of the biggest breakthroughs that green chemistry has yet encountered. Okay, let's continue with solvents, and this time move on to supercritical fluids. I don't need to remind you what they are. This is a generalized pressure temperature phase diagram, and so you increase the pressure, you increase the temperature, and okay, you have the triple point there, but you continue up the curve. There is a point at which the density of the liquid is the same as the density of the gas, and at that point you have another area, you have solid, liquid, gas, but now you have supercritical fluid. And basically, to get a supercritical fluid, you need to be above that critical point in terms of temperature and pressure. There are a number of supercritical fluids, common supercritical fluids, and here, if you like, are the critical points of those substances. Okay, so let's actually look at some examples. Now, okay, supercritical fluids were really thought about properly from the mid-80s, but even before that, there were some processes that ran above the critical point for those solvents. The Haber process is one. It runs above, it's the nitrogen-hydrogen process to make ammonia. It runs above the critical point of ammonia. The low-density polyethylene synthesis, high temperature and pressure, free radical polymerization. Again, effectively you had a supercritical liquid process there, but it wasn't necessarily called that at the time. They were just the conditions for the process. So you can use supercritical fluids as solvents, as reactant solvents, so that they actually are part of the reactant system, or as extractants. Now, you have a number of advantages of using supercritical fluids. Very high density and low viscosity, so you can get good conduction properties. You can fine-tune solvent properties. Usually there's a large window of temperature and pressure adjustments you can do in the supercritical zone, which changes the properties, and we'll look at an example of that in a moment. And it's usually relatively easy to recycle supercritical fluids. Okay, so let's now look at carbon dioxide as a supercritical fluid, simply as an example of a supercritical fluid. And of course, for carbon dioxide, it's non-flammable. It's a very good solvent for small polar molecules and gases. And supercritical carbon dioxide is actually accessible at low temperatures. Applications: decaffeinated coffee. You can use it with hydrogen actually to do hydrogenations. Note exothermic reactions. If you have exothermic reactions, that's something with supercritical fluids you have to watch quite carefully, because you don't want to be either it's not so much going out of the supercritical fluid range, it's actually runaway thermal reactions. So supercritical carbon dioxide has now dissolved most of the nasty CFCs that were used in dry cleaning plants. With polymerization reactions, by changing the pressure, typically you're changing the properties, and you can then end up with different optimum relative molecular masses of your produced polymer. So lots of applications. We'll look at a few more, and I'll go quickly through these. Again, I refer you to Lancaster for these. A free radical initiator like AIBN, you can actually tailor make. You keep everything in solution. You put your surfactants in there to stop it all falling out. You don't have cage effects in supercritical fluids. So you can tailor make effectively the relative molecular mass of your polymer. Really powerful. So now you're not getting a whole range of molecular masses in your polymers. You're actually able to engineer it to where you want it to be. You don't get loss of free radicals, and effectively that's how PTFE and some of the design fluorinated polymers are made. Supercritical carbon dioxide is both the reagent and the solvent in these systems. Okay, other clever chemistry with supercritical carbon dioxide: a nice asymmetric catalytic reduction using a a rhodium organometallic catalyst. PP there is this double ligand there. Then very neat, very clean, and very safe. Now, with most of our examples are on supercritical carbon dioxide, I'm going to look at supercritical water as well, because it leads us into our final slides on the biofuels case study. Because supercritical water is a lot less accessible, you're up at close to 400 centigrade and 700 atmospheres. It's not really used as extensively. It's also corrosive to steel, which doesn't help. It's been predominantly used for mineralogical syntheses, quartz, mobile phone gemstones and stuff. However, there's been a recent use in biofuels, so it's a nice bridge to think about this. So we're now going into our final little mini case study. So this technology has two applications, a supercritical water, both of which are part of the biofuels case study. Improvement of water quality in pastoral farming areas, really important for pastoral nations. Obviously New Zealand is one of them, the UK, the US. Reduction in carbon dioxide emissions from either industry or farming, using either carbon capture and storage or using farm effluent, and the production of biofuel or hydrogen. These are particularly important in energy resources type studies, and in that module we're looking at these a little more closely. In all of the cases, what do you need to do it? You need a concentrated source of CO2 or agricultural effluent. So let's look at the process, and we'll start with the agricultural effluent, because this has the application for water purification on dairy farms, for instance, and the like. So we have our waste effluent coming in here, your cow shit or whatever it is you're using. You have a solids removal plant, and the solids then are anaerobically digested. You can produce fertilizer out of that. You can produce methane, biogas, which you can use in a generator to get heat and power. The exhaust gases from the generator, carbon dioxide, actually get passed into the same place where the liquids, the nutrient liquids, the wastewater are passed, where you have algae growing. And this you may think this can be a sort of glass in-house plant. It can be shallow ponds, and I'll show you some examples in a moment. The algae is then harvested, and the output from that is treated water, clean water. The algae that you've harvested is then used to make biofuel and fertilizer. The biofuel is refined and then used. So all in all, you're taking either industrial effluent or agricultural effluent, and you're producing products out of it, you're reducing impact, and you're producing energy out of it. So it's actually quite a cool proposal. And this is not some sort of vague research. This is now pilot. There are pilot plants out in New Zealand dairy farms, for instance. It's now commercial. It's not yet fully commercialized, but it's on that road. So first of all, you need a concentrated source of carbon. Okay, here's an intensive dairy farm, not in New Zealand. That's elsewhere in the United States, and so it's quite easy and straightforward. I don't like the idea of cows like this, but I suppose this module's not about that. But you have systems to gather their shit as well, and their the other effluents that they produce. I said previously that the algal reactors don't have to be sort of fancy posh things in factories. These are algal ponds. Shallow ponds are being fed agricultural effluent to grow algae. These actually are in Christchurch in New Zealand, and in fact in my previous life, this is Christchurch. This is one of the oxidation ponds, major wildlife reserve. In fact, looking from my office window, my office is actually behind this photograph. I could see that in the distance. So my office was quite close to these this project, where this project was running. But you see, you haven't got, once you've got the ponds and normal sewage treatment plant, actually there's things you can do here. You might ask, well, okay, how do you process the algae? Well, the algae processes the CO2 and the nutrients and the water to make their own cells, and they produce lipids. Now, effectively, these lipids are pure biodiesel, but getting them out of the cell is really, really difficult. You can't filter them. The energy required is huge, and you don't want to be wasting energy. The way this is done is the algae is actually, you can use quite clever concentrated techniques to have a concentrated algae stream in the water, and then you run it through a supercritical water reactor. It very cleanly breaks this up and separates the biodiesel from just about everything else. It's a very clever sort of reactor. So okay, let's just look at the other type of application, flue gas, carbon dioxide. Here what you're doing, you're producing concentrated CO2 and you're producing methane gas and therefore energy. So in it goes from your stream. You form in your bioreactor, you form your organic compounds and water, dewaters it, and then goes through. You make those organic compounds, you produce methane, which you can then burn. You burn fine and produce concentrated carbon dioxide there. The methane gets recycled through a burner, which gives you heat, and the CO2 and the nitrogen go back through the bioreactor. Likewise here, your nutrients in your water from your dewatering stage go back into your reactor. So it's all nice closed loops. So we talked a bit, not so much in this module actually, but in energy resources. Can we, is the question we ask as chemists very often. The question we should ask more carefully and more often is, should we? So we've got an economically viable technology that cleans up the environment, produces energy, and makes farms more viable. That one actually is quite easy. It's not really a very difficult solution. And I imagine that technology will be rolled out internationally in the fairly near soon, providing the company doesn't get gobbled up by a large multinational, which is what tends to happen to New Zealand companies. Okay, last slide, I think almost the last slide. The other way, of course, is to use ethanolamine in carbon capture and storage to then use that concentrated carbon dioxide using one of our old friends, a zeolite, and a hydrogen zeolite, so you've got H+ in there, to produce your organic compounds. Or you can use your carbon dioxide using it to make syngas, which then you can use Fischer-Tropsch, or of course via algae. So a whole number of routes to make biofuels. I'm not going to talk about, we've done quite a lot of work on the economics of Fischer-Tropsch. I'm not going to talk about that here. I will talk about it in energy resources. Okay, so this is the last slide. Summary of the case study is actually fossil fuels are getting cheaper, which means it's harder now to make biofuels. But there is now good and efficient technology available, where if the biofuels are side products, that you're doing other things, you're making your process cleaner, you're making it safer, you're maybe cleaning up the environment, then actually this stuff will still fly. So potentially it's a happy ending. Anyway, you've listened to me long enough. Thank you very much. And yes, I look forward to seeing you soon. Take care. Bye bye.